So take a look at the complementary supplementary angle worksheet. Now that I have you terrified in making definitions, we're going to come up with a whole bunch more. Now that you doubt that the Earth exists, or that any of this is actually real, if you were Descartes, I doubt, therefore I might be. Okay. Yes. Okay, so how do you define an angle? Well, we have to be able to state what an angle is before we can describe what kind of angle it is. So there's an angle on your paper. Not there. Up there. That's an angle. How is an angle constructed? What's it made out of? Two rays that share a beginning point. That would be the definition. Now, when we say angle, most of the time we mean the interior. Okay? You can describe an angle bigger than 180, but most of the time we don't. We're not going to include that in the definition. So for the next little while, we're only talking about interior angles, the smaller side, because that's like a 40-degree angle, and it's also a 320-degree angle. So for now, we're going to ignore the exterior and only deal with the interior. Okay? So an angle can be named in four ways. The vertex could be listed as point, I don't know, A. We could call this angle A. And make sure it's not less than A. There's a difference. The angle has a flat side, a horizontal side, and less than does not. Okay? But naming an angle by its vertex is only applicable if there's only one angle for that vertex. If I were to draw a second ray or a third ray, angle A ceases now to exist because there are actually three angles there. Four if you include the exterior. So you don't know which one we're talking about. Okay? You can also number or letter the interior of an angle, and we could call it angle 1. But the most common way to name angles is to put points on the rays, and we would do angle BAC or angle CAB. What about the other combinations? Why do those not work? Right, the middle letter describes the vertex. Okay? Going down to degrees. How do we define a degree? Measurement. What type of measurement is it? So a length is measured as a distance or a width or something like that. Is an angle a width? Okay, so if I said walk 1 degree, could you do that? No. There actually is a way to measure angles that allows you to both walk and do whatever the other thing is you haven't come up with. And we'll learn that at the end of the year. So what is a degree? Where does it come from? So every measurement can describe movement. What sort of movement are we describing? There are lots of ways to say it. Wow, I really stumped you. I'll just let you sit in agony. Keep thinking. What do angles do? What do degrees do? Okay, open. It's not a distance, though. It's not at all a distance. But so if I had a little angle and I had a big angle and I start measuring distances, those are the same angle regardless of how long the sides are. So what's the movement um, dealing with angles? What? Rotation. Right. It's just a rotation. Spin would have worked. Lots of other things. So a degree is a specific rotation. 1 degree, regardless of how big the object is a specific rotation. How much of a rotation is 1 degree? 1 out of 360 parts of a circle. Hey, I haven't even written it yet. You're behind and I haven't even got there. So, a degree is 1/360th the rotation of a circle. We also could have defined it as in terms of the rotation of a straight line. How would that change the definition? Yeah, if we instead of doing a whole circle, what if we just described the rotation across a straight line from one side of the line to the other? 1 out of 180, right? So either way would work. So now that we've defined angle and degree, let's define a right angle. What is a right angle? A 90-degree angle. Yep. Back 2,200 years ago or so, Euclid did not use the word degree. In fact, he only measured one angle. In all 47 proofs of the Pythagorean theorem, he used angles all the time. And in just about every proof he said this angle is congruent to that angle, but he never measured how big they were. The only angle he ever measured was a right angle, and he defined right angle, but he didn't use the word degree. That does not exist in his book. So how would you describe a right angle without talking about the degree? And here's a hint. The word perpendicular doesn't work. Okay, so if we did the angle formed by a vertical line and a horizontal line, that works, right? If you have a perfectly vertical line and a perfectly horizontal line, you create a right angle. But our definition has to include all right angles and exclude all non-right angles. Does that include does that include all right angles? No. It does include one of them, but not all of them. Okay? So if I were to tilt that figure a little bit, all of a sudden the definition no longer works. Yes, sir. Right, and that's what he did. Well, actually, Euclid didn't use that. He did this. He said when one line intersects another line and those two angles are equal, they're both called right angles. So what we're going to say is the angle created, I better write this down, and I like symbols, the angle created when two lines intersect in such a way that all angles are equal or congruent. Congruent. Oh, 90 degrees is so much easier. All right. So if we look down, we're now going to define a bunch of different types of angles. The first one is adjacent angle. I've given you 4 figures. The first one represents adjacent angles, and the other 3 do not. So we're going to come up with a definition by looking at a series of a yes and a series of no's. So what are the qualities that adjacent angles have or do not have? They share a vertex. So if you look at figure 2, the difference between figure 1 and figure 2 is they share a vertex. So adjacent angles are angles that share a vertex. What else do they have? So you say share an entire ray? That would work. But um, what do we call those in angles? Well, what do we call this? I almost said it. What are the rays inside angles actually called? No, what? Sorry, this is not a difficult question. What is that called? It's a ray, but what is the structure of the angle called? It's the same thing we call I almost said it again, the structures inside polygons. Sides! Yes, they share a side. Oof, sorry. Yes. So figure 4 is thrown out because it doesn't share a side. What about figure 3? I think I heard the word a minute ago. So they share a vertex and they share a side. There's one more qualification to be an adjacent angle. No, it has nothing to do with their size. Right. Angle 1 is inside angle 2. And in angles, we use the words interior and exterior. Interior is the small side and exterior is the big side. So we could say that one is not interior to the other, but we probably want to say that are exterior to each other. So and are exterior to each other. No. Okay. So now we know adjacent angles. Moving on to complementary angles. What does it mean to be complementary? So let me draw you a set of complementary angles. Those are complementary. So they're angles that add up to 90 degrees. Anything else? They are adjacent. Do they have to be adjacent? Can you ever think of a time where they won't be adjacent? So if I just had a random 30-degree angle and a random 60-degree angle, and they add to 90, is that worth knowing? So should we put that in there? Okay, you have forgotten the cardinal rule of writing definitions. Do I need it? No. Is it going to hurt by putting it in? Probably not. I cannot think of a time where you will have complementary angles that are not adjacent. I don't know of any. But, no, we don't need it. It doesn't do us any good. It doesn't add to the definition, so we leave it off. Yes, so complementary are just angles that add to be 90 degrees. And with complementary angles, it doesn't really matter. We could have thrown the adjacent on, but maybe there's a case I'm not thinking of and you're not thinking of. And if we don't actually need it to describe complementary, then we leave it out. So what about supplementary? Add to 180. Do we need to put adjacent in? No. Do we need to leave adjacent out? Yes. Because if I have this picture, A and B are supplementary. Everybody agree? But what if I had a set of parallel lines? Are A and B still supplementary? Yes, they are. Is that fact ever used? All the time. So if we were to add adjacent to the supplementary definition, then this would cease to be supplementary, which is bad because we need that all the time when dealing with parallel lines. So supplementary are angles that add up to 180. But is it good to know that something is both supplementary and adjacent? Yes. A lot of the time it's good to know. So instead of changing the supplementary definition, we write a new definition called what's it called? Linear pair. The next one on the list. So, linear pair is a set of angles that add to be, don't write this down, a set of angles that add to be 180 that are also adjacent. There's an easier way to say that. Adjacent supplementary angles. Yep. Why don't we write, or why don't we create a new definition for right angle pairs? Because complementary really only applies if they are right angle pairs. This parallel idea, you don't actually need, you don't need complementary when you're talking about parallel lines and transversals. So, as far as I know, there's no reason to make that definition. It certainly isn't going to come up in this class, but we still leave adjacent off of that definition because who knows? It might screw something up later. Okay, the last one is vertical angles. What does it mean to be vertical angles? Can I give you a hint? Which angles are vertical? The ones opposite. And so this angle equals that angle, and this angle equals that angle. So how would we define that? Let me start you out. Angles created when two lines intersect. Well, that's kind of given, right? It's always going to be 360. So how do we describe the top and the bottom angles, or the left and the right angle? We could say opposite, but we've used opposite before. At least we've talked about opposite before. If we have a parallelogram, opposite means those. So in that case, opposite are angles that are on opposite ends, and they don't share anything, really. But we don't really want to use opposite in this case because it's different. So we have created the word adjacent. Could we use the word adjacent to describe vertical angles? Are they adjacent? So they are? So the definition of adjacent is they share a vertex and they share a side. So the top angle and the bottom angle, they share a vertex, but they don't share a side. Right? They're on the same line, but remember, a side begins at the vertex. So if they're not adjacent, how would we define that? Not adjacent. So non-adjacent angles created by the intersection of two lines. So vertical angles are non-adjacent angles created by the intersection of two lines. And by lines, we also mean segments and rays. The intersection of two lines. Okay. Name the marked angle in as many ways as possible. So how do we name the first angle? Angle D, or angle 6, or angle GDM. And don't forget the angle sign. I will dock you if you miss the angle sign. And angle MDG. Okay? How would we name the second angle? Only the marked angle. So angle QWT, or TWQ, or what about angle W? There is no other way to name it. Angle W doesn't work because angle W actually represents more than one angle. Because there's multiple angles on that vertex. Everybody all right with that? Okay. So, which one? Oh, sorry. Let me go back. So, we're just talking about this angle here. It only has two names. QWT and TWQ. You can't call it W because W has two angles. And it doesn't have a number. So, those are the only ways. Sorry. Okay. So now we're going to look at a set of angles and we're going to determine which definitions does that set apply. For which definitions does it apply? So the first one, they are supplementary. Anything else? Go ahead and abbreviate. Don't write the whole word out. Yes. They are adjacent, which means they're also a linear pair. If you're supplementary and adjacent, then you're automatically a linear pair. So that one fits three definitions. Okay, the second one, vertical. Anything else? No? Okay, the third one, complementary and adjacent and that's it. Yep. Okay, I'm letting her get caught up. Stay with us. All right, number 4, supplementary. Anything else? No, they're not adjacent, so they can't be linear pairs. And if you're supplementary, you can't be complementary. So, yeah. Fifth set. None of the above. They might be complementary, but I doubt it. They're certainly not supplementary, but it looks like B is really close to 90 degrees. And the last one, just vertical, nothing else. Okay. Find the value of x. How are we going to do that? Right. Those two angles are supplementary, so if I add them together, they should equal 180 degrees. So, x plus 143 equals 180. We're going to subtract 143, and I get x equals 37. So, for the next one, what do I know? We know those two angles are complementary, so 4x plus x equals 90. So 4x plus x is 5x equals 90. X equals 18. But you need to be careful when you take tests and they have questions like this. My instructions asked for the value of x. What if the instructions asked for the value of the two missing angles? I need to plug x in, so the small one would be 18 degrees, and the bigger one would be, well, they're complementary, so 90 minus 18 is 72. Mine says find the value of x. Okay? Well, if I asked you for the value of the missing angle on the next one, what would you say? It's 60 because they're vertical, so I don't even need to do anything. But if it asks for the value of x, then you need to set them equal to each other. 5x plus 15 equals 60. Subtract 15, subtract 15. 5x equals 45. So x equals 9. And if you plug 9 back in, you'd get 60. But you wouldn't need to. The last one's a little bit tricky. Those angles are not adjacent, so we have sort of a problem on our hands. Okay, so Kelton is saying, hey, I'm going to state this as 119. How does that help? Well, I don't need to move anything anymore. I now have a straight line. So this would be called a linear triplet. But if you did it a different way, that's fine. What if I move the 40? Do I still have a straight line? Yes. What if I would have moved the 2x minus 5? So you could have moved any one of them, and you would have had the same formula, which is 2x minus 5 plus 119 plus 40 is equal to 180 degrees. So I'm going to subtract 40, subtract 119, and add 5. 180 minus 40 is 140 minus 119 is going to be 21. Add the 5, 26. So 2x equals 26. Divide by 2. X equals 13. What if I asked you for the size of the missing angle? You could do 180 minus 40 minus 119, or we could plug 13 into 2x minus 5. 2 times 13 is 26, minus 5 is 21. Yeah, so however you wanted to do it, that would actually work. All right, your assignment tonight is to finish that worksheet.